that's why you can't find it. That's my fault. I actually, I'm glad you brought that up. I totally did that. All right, guys, I hope everyone's had a good Thursday so far. Today I was just going to use today to review everything pretty much we've done this week. There's no new material today. Also, there won't be any new material tomorrow. I want to spend time to make sure we're good with like finding these intervals of increasing and decreasing, the intervals of concavity, and then finding key points in the graph, like the points of inflection, and then the relative extrema. So I am going to fill out a notes packet. We're not going to do all the questions on it. If you look in OneNote, like I've linked to the actual Word document there. There is an answer key to the problems that are assigned, but I'm not, again, assigning it. I'm just going to kind of use it for notes. So yeah, I'm going to go ahead and just jump into it. So this week we have talked about basically one way we can use the derivative is to find key portions on the graph. The first things that we of course talked about is how we can find intervals of increasing and intervals of decreasing. We know the big idea if you're finding intervals of increasing and decreasing is you are looking at the sign of the first derivative. So how I have these notes kind of laid out, we'll talk about like what's the big idea for each of these topics, and then what is the justification you would use for the two things, and then the steps. So like if I wanted to prove that my function was increasing, we know that's of course where the derivative is greater than 0. If I was showing where my function was decreasing, that is where my derivative is less than 0. And then the steps, pretty straightforward. You first had to find what we call the critical points. And the critical points are where the derivative is equal to 0, or where the first derivative is undefined. And then once you find those critical points, you're going to use those critical points and the first derivative to do a sign chart with that first derivative. And that's what we talked about just on Monday. So instead of looking at things graphically, we could do it algebraically. As an example, I'm not going to do it in class, but you're more than welcome to do it on your own for practice. It's on that next page in the notes, but I have a function, and I asked just like find the intervals of increasing and decreasing. Again, I'm not going to do it in class, but if you want to do it for extra practice, the key is posted along with all the homework answer keys. It might be a good problem just kind of to save and review, like, I don't know, like on Sunday before your quiz on Monday. But we're not going to do that in class. But that is when you can go back and practice to find intervals of increasing and decreasing. And then on Tuesday, we talked about intervals of concavity. We know the big idea if you're looking at concavity is we're looking at the sign of the second derivative. We know that when the function is concave up, that means the second derivative is positive. It's concave down when the second derivative is negative. Did want to kind of redefine the point of inflection for you. So we know the point of inflection is where f double prime changes sign. A common mistake I often see is people want to say the second derivative is where, or excuse me, the point of inflection is where the second derivative is equal to 0. That's not necessarily the case. So if you're looking to identify a point of inflection, you're going to have to look at sign changes of the second derivative. And so the steps, though, are pretty much the same. We don't call them critical points when we deal with the second derivative, so just kind of like key points. But we basically want to find where the second derivative is equal to 0 or undefined. Those are basically the function itself is either non-existent or basically not concave up nor concave down. And then whether you want to do intervals of concavity or a point of inflection, you're going to do a sign chart with that second derivative. Some other like hints I know when you're doing this problem, like since you are doing the second derivative, it's often easiest to like if you can simplify your function first, or simplify your first derivative, it makes it easier. I also, if I have to use the second derivative, I often try to avoid the quotient rule, just because like solving a problem after the quotient rule can just make it a little bit more complicated. So that's what we did on Monday and Tuesday. Wednesday, I'd asked you to review the extrema. So looking ahead of your notes, again, I have another example dealing with a point of inflection or concavity. I'm not going to do that one in class. I will save it for you if you just want to do it on your own for the extra practice. Again, the key is posted in the answer key folder. I did want to spend some time, though, with relative extrema, just to make sure we understood how we justify relative extrema, and then we will look at these two examples. So in calculus, we have two ways to determine whether we have a relative minimum or a relative maximum. The first method, I think the one that's like the most intuitive to students, is what's called the first derivative test. And the first derivative test, it relates to sign changes of the first derivative. And the steps to doing the first derivative test are the exact same steps of finding intervals of increase and decrease. So like you first have to find your critical points where the first derivative is equal to 0 or undefined. And then you have to do a sign chart with that first derivative. And the way I think about the first derivative test, so we know what possible maximums look like. We know what a possible minimum looks like. And if we're looking at a relative extrema, you just kind of think logically, well, how does a point end up being like a maximum or a minimum? If it's a maximum, then it probably means you went up to the function and then you went down. So it has like a positive slope, and then that changes to a negative slope. Where if you have a relative minimum, you have negative slopes, and then it changes to a positive slope. So whenever you're justifying using the first derivative test, you just want to like how it's changing, and that's how you know you have a derivative, a relative minimum or maximum. So we know that x equals a is going to give a relative maximum if f prime changes from, should have written a little bit smaller, positive to negative. So again, we know we have a maximum if our derivative changes from positive to negative, because logically that means your function is going from increasing to decreasing. Likewise, x is equal to a is going to give a relative minimum if f prime or y prime, whatever you want to call it, changes. So you have to go down first and then up. So changes from negative to positive, and that's going to give you a relative minimum. And so I did want to do this example. So on the next slide, I have just a simple function, just so we can kind of see the process of how we would find an extrema and then how we would justify it correctly. And that would be what we call the first derivative test. Any questions so far on anything? All right, so let's go ahead and look at this first example. So I have a function. I want to find the x-coordinate or coordinates at which the graph of y is equal to x to the fourth minus 2x cubed plus 8 has a relative extremum. And I want to also classify those as relative minimums or maximums using the first derivative test. Well, if I'm using the first derivative test, I kind of clearly first need to find the first derivative. So x to the fourth becomes 4x cubed, minus 3 comes down in front with the 2, new exponent is squared, 8 goes to 0. And again, solving this, we're going to set it equal to 0. There's no denominator, so there's not really going to be a place where the derivative is undefined at. And so we can see we do have some critical points on the graph, Those critical points are at x is equal to 0 and x is equal to 3/2. So now I can go ahead and create my sign chart. So similar to how we did, not similar, but exactly how we did intervals of increasing and decreasing, a sign chart is a nice way to kind of show our work in order to prove whether we have a relative minimum or a maximum. I have my factors going down the side. And then I like the vertical line here as kind of dividing points. 2x squared, though, is a nice one. If I have 2x squared, I know that that is always going to be positive. And then for 2x minus 3, anything less than 3/2 if I plug that in. So like, think of any number, I'll choose 0. 2 times 0 minus 3 is negative. So anything on the left will be negative. Anything on the right is going to be positive. So overall, what is this first derivative? The first derivative is negative, negative, and then positive. So if we're looking for relative extrema, we do have two critical points. Again, they could either both be extrema, none of them could be extrema, or just a few of them could be an extrema. In this one, we have one possibility at 0. 0 is not anything important because we see on both sides of 0, the derivative is negative. So like it's basically decreasing through 0. But we can see at 3/2, it has a negative derivative and then a positive derivative. So we can see that at 3/2, we do end up having some sort of minimum. So I do want to answer that and then justify my answer. So I can say something like f has a relative minimum at x is equal to 3/2. How do I know that that's a relative minimum? Because f prime changes from negative to positive. Notice when you're justifying an answer using the first derivative test, I will not require it, and neither does the AP exam. You don't have to say like by the first derivative test. As long as you state the requirements of it, then that's good enough. So I've stated that I have a relative minimum there. So that's important. I've identified it and classified it. I've stated the x value clearly, and then I gave my justification. X equals 0 is not anything again because the sign does not change at that point. It is still a horizontal tangent, it's just not an extrema on the graph. One thing I do want to remind you to be careful with, you never want to say there is like a relative minimum is x equals 3/2, because the relative minimum isn't 3/2, it's just at 3/2. So like when we talk about like what is the relative min or relative max, we're actually going to be talking about the y value and not the x value. So saying at works or like gives works, but we don't want to say is when we're talking about that problem. Questions about the first derivative test? All right, so then we have the second derivative test. This is often the one that I think takes students like a little bit more time just to kind of like absorb and make sense of it. Like it's not the most intuitive one. The big idea with the second derivative test is you are looking at the concavity at the horizontal tangent lines. And so the second derivative test does have kind of like less cases you can use it because it doesn't work when your first derivative is undefined. It only works when your first derivative is equal to 0. So basically the idea behind this is if you have some function and you know that it has a horizontal tangent line, in order for it to be a maximum, that function is going to have to bend downwards away from that tangent line. Likewise, if you have something that's a minimum, so imagine that this point's a minimum and we know that it has a horizontal tangent line. In order for it to be a minimum, that function is going to have to bend upwards at that tangent line, and it's going to have to be concave up at that location. So the justifications for the second derivative test do have two parts that you have to mention. If it's a relative maximum, you have to state clearly there you have a horizontal tangent by stating that f prime of a is equal to 0. And you have to state the concavity at that place too. And so the concavity, if it's a maximum, is concave down. Think that your graph is bending downwards from the tangent, so the point would end up being a maximum. For a relative minimum, you still have to again state that there is a horizontal tangent and that the second derivative is greater than 0. Some students often ask the question, and you might be thinking the same thing, like, why do we need a second derivative test if we have a first? Like, if you can do the first perfectly well, then honestly, then that's probably the one you want to choose. I will say, though, with the second derivative test, like, there's going to be cases where the first derivative test is next to impossible to do. So we haven't really looked at them yet in this class. They're coming up in about, like, a week and a half. But there's going to be some functions where it's literally impossible to make a sign chart for that derivative. And so the second derivative will kind of take over, because one nice thing about the second derivative is you do not have to make a sign chart. But again, one negative part about the second derivative test is you do actually have to find the second derivative. So the steps for the second derivative test is you first need to find where you have horizontal tangent lines. So you're going to find where the first derivative is equal to 0. If the first derivative is never equal to 0, then you cannot use the second derivative test. It doesn't mean that there are no extrema, and that's another important thing to point out. It just means you can't use the second derivative test. It's inconclusive if you have no horizontal tangent lines. And then after you find where you have horizontal tangents, you're going to plug those x values into the second derivative. And one thing that will help you in the long run, you don't necessarily have to find what the actual value of the second derivative is. You just need to know, is it positive or is the second derivative negative? Questions on that before we look at the example with the second derivative?
When would y prime never equal 0? Like, when would it not equal 0?
So for example, if you have a graph that looks like this, that has a cusp there, the second derivative does not equal 0 there, but that is a relative minimum on the graph. And since it's a relative minimum, like the second derivative wouldn't be able to justify for you that that is a relative minimum. So if you had a case where that would look like that, you would actually be forced, like the second derivative test fails, and you would be forced to use the first derivative test. If that answers your question.
Yeah.
And that is, like, I'm glad you asked that, because again, it's like, it is a common mistake, like the second derivative test only works when you have a horizontal tangent, whereas the first derivative test can work when you have horizontal tangents and like places where the derivative is undefined, like a cusp bar corner. Another time say it one more time.
What would it look like if you like wrote it out like as an equation?
You wrote it out as an equation. I'm trying to think what I think you mean. So like if you have a first derivative that ends up looking like this, like that just happens to be your first derivative. This derivative is going to come from a graph that has a cusp or a corner from it. And so like that would be a part where like y prime can never be equal to 0 in this case. And so that would be a problem you would be forced to use the first derivative test on.
Okay.
Does that help?
Yeah.
Another case, though, I do sometimes like doing the second derivative test over the first derivative test is examples with trig. Not always, but sometimes, especially if you've done the homework, you've probably noticed that sometimes doing a sign chart with trig is just like a little bit more complicated. Like you have to think about like the radians and kind of where things are positive or negative. And again, one benefit of the second derivative test is you don't need to use a sign chart. So for this last example today I just want to find the x coordinates of extrema just on the interval from negative pi over 2 to pi over 2. So basically we're thinking about like the unit circle, basically that right-hand side of it, where this graph of tangent of x minus 4x plus 4 is going to have relative extrema, and I want us to use the second derivative test. So first part, even though it's called the second derivative test, the x values are coming from the first derivative. We want to figure out where this function has horizontal tangents. So we do need to find the first derivative first. Derivative tangent is secant squared. The derivative of 4x is just 4. That plus 4 is going to go to 0. And then horizontal tangents, so I don't need to worry about where this is undefined. Horizontal tangents are only where it's equal to 0 at. So I have like secant of x would be equal to plus or minus 2. I added 4 to both sides and took the square root, making sure you remember that plus or minus. If you remember from last year, I often don't solve equations in terms of secant. I like dealing with terms of sine and cosine. So since secant is the reciprocal of cosine, if I say secant is equal to plus or minus 2, that's the same thing as cosine is equal to plus or minus 1/2. So then within that interval, when is cosine equal to plus or minus 1/2? Well, we're only on that right-hand side, so we're only looking at where it's positive. We get x is equal to pi over 3. The other angle is 5 pi over 3, but 5 pi over 3 is not within that interval. It's outside of pi over 2. So the angle I'm going to choose instead is going to be negative pi over 3. So those are the two places where I have a horizontal tangent line. And again, the idea behind the second derivative test, because the conceptual part of this is just important as like being able to do it, is if we have a tangent line, we basically want to figure out, hey, is that function bending upwards above that tangent line, or is it bending downwards below that tangent line? That can kind of help you figure out if you have a minimum or a maximum. Well, if I need to figure out which way it's bending, let's go ahead and find the second derivative. So y double prime, make sure you use the chain rule here. This is secant squared. So the 2 is going to come down in front. The inside stays the same. The new exponent is the 1 times the derivative of the inside. The derivative of secant is the product of secant and tangent. I'm going to clean this up to make it a little bit easier for us. So my second derivative ends up being 2. Secant times secant is secant squared times the tangent of x. So again, why is that second derivative used? We want to figure out whether my function is concave up or concave down at those horizontal tangents. So I'm going to go ahead and plug it in. Let's go ahead and just plug in. Doesn't matter which one you plug in first. I'll choose pi over 3 because I wrote that one down first. And again, I kind of cheat, like I don't necessarily evaluate this as long as I can figure out clearly whether it's going to be positive or whether it's going to be negative. So if I'm plugging pi over 3 into my second derivative, I know that, well, 2 clearly is always positive. If I have something and square it, it's always positive. Pi over 3 is in the first quadrant, so tangent is also positive. So I know that my second derivative at pi over 3 is greater than 0. So again, we know now so I have a horizontal tangent at pi over 3. The second derivative is greater than 0, so it's concave up. So I know now that there is actually a relative minimum at this point on the graph, and we'll justify it formally in a second. And then I can do the same thing for that other coordinate. So plugging in negative pi over 3. Again, I don't have to evaluate it as long as I can determine what the sign of it is. 2 again, positive. Secant squared, that's going to always be positive. And this was negative pi over 3 that I plugged in. Negative pi over 3 is in the fourth quadrant. In the fourth quadrant, tangent is negative. Well, in my second derivative, a positive times a negative is negative. So now I know that my second derivative is concave down. So I knew I had a horizontal tangent line, but my function is bending downwards. so I know that I have a relative maximum there. If you got the second derivative was equal to 0, then the second derivative test fails and is inconclusive. So when we say it fails, it doesn't mean that there's not a relative min or relative max. It just means that it's inconclusive and we don't know what that coordinate is. So if I'm justifying my answers, so we have two things that we have. So I have x equals pi over 3 is going to give me a relative min. How do I know? Because, and I have to make sure I include both statements, y prime of pi over 3 is equal to 0, and y double prime of 3 is greater than 0. You have to include both statements. For example, if you just said you had a horizontal tangent, well, that's all that means. You just have a horizontal tangent there. If you just stated the second derivative was positive, then you only told me that's concave up. And we know that a graph could be concave up and not necessarily have a relative extrema there. And I can do the same thing for negative pi over 3. It is giving a relative maximum. How do I know it's a relative maximum? Because the first derivative there is 0. And the second derivative at that point is less than 0. So those are the main kind of things we'll use for right now, I should say, not the main thing overall. But for right now, what we'll be using the first and second derivative defined. We'll see that this will eventually expand to lots of other concepts. So right now we're just talking about in terms of functions. But next week we'll expand this and talk about how we can use this to expand it to things like position, velocity, and acceleration. And then in the next unit we'll expand to talk about how we can just expand this idea to just talk about like maximizing things in general or finding the minimum of things in general as well. And that's when we start getting into the word problem part of calculus. But any questions on that second derivative test? All right, so your assignment, that's basically the end of the notes, but I did want to be a little bit clear on the assignments. So far I have assigned homework 1 and 2. Yesterday I assigned homework 3 after you should have watched that video dealing with the relative extrema. And so homeworks 1, 2, and 3, if you do those, then that's basically going to prepare you for your quiz, which is on Monday. Tomorrow is just going to be a work day. I am also, though, assigning homework 4. So at this point, we are able to do actual free response questions because now we have enough background in calculus that we can actually do a full question. But I will not be grading homework 4 until the day of your test. I just feel like with those 4 assignments, you probably have a lot going on already. So like if you can't do number 4 before the quiz, like that's fine. I'm only checking homeworks 1, 2, and 3. But if possible, I do think homework number 4 will help you on the quiz because everything on homework 4 is still on the quiz. So those are the assignments that you have. Again, make sure you're asking questions if you have them. I did finally get uploaded the worked out problems for each of those. I will say I do not have worked out problems for number 4, but since those are AP problems, what I did post is the actual rubric that the College Board would use to grade those with. Just so you can kind of compare your work with what College Board expects you to show. So with that being said, like class is over if you wanted to sign out of the live meeting. If you want to hang back and ask any questions, that's fine as well too. Because I won't end the meeting until class ends.